This is Nina Mehebi with Lab 9, Energy Transfers for Spring Motion. In this lab, we were instructed to analyze and model the motion of a spring from a video, and then study the transfers of different forms of energy. Our results show that in accordance to the energy principle, total energy was conserved. However, energy was transferred between spring potential, gravitational potential, and kinetic energy. The first step was to track the motion of the spring in the video using tracker. For the origin, I use the origin of the spring. My negative y-axis is along the axis of the spring in equilibrium, and I set the calibration stick length equal to the length of the spring in equilibrium, which we knew was 0.7 meters. I then tracked the motion of the mass at the endpoint and exported the position data to an Excel file. For Python, we now have to initialize all of our variables. The mass we were given is 0.402 kilograms, and we obtained the initial position from tracker. Because we started the video from when the mass was at rest, the velocity is obviously 0. Next, we have to initialize the interaction constants. G is a given. It's known. It's the gravitational constant of Earth, which is negative 9.8. And to solve for Ks, we first had to find the period. We found that by finding 2 points that were at approximately the same position at different times and calculating the time between the two. We found that it was approximately 1.152 seconds. This value represents the period, the time it takes to go through one entire oscillation. We then divided this value by 1 to get the frequency, which we found to be 0.658. Using the frequency, you can solve for angular frequency, which is equal to 2 pi over just the frequency. Using this value, we can solve for k because omega, or angular frequency, is equal to the square root of k over m, and m is known, and we now know omega. So using the value of k, we solve for L naught, because at equilibrium we know that the force of gravity is equal to the force of the spring. Because we know this, we can say that mg is equal to ks. And because we know the values of L, which is 0.7, and mg, as well as now k, we can solve for L naught. We also had to initialize the gravitational potential energy, which is just mgh, and kinetic energy, which is 0 at this point because it has no velocity to begin with. The remainder of calculations take place in a while loop that goes for the duration of our tracker video, which is 8.452 seconds. So for each time step in this interval, the following calculations are made. The force of gravity is found, negative mg. The stretch of the spring is found, L minus L naught. And the total force is computed, which is theoretically only the force of gravity and the force of the spring. We then use the momentum principle to update the velocity, and use this to update the position. Also, for each time step, we want to calculate the different energies acting on the system, or present in the system. So we first store their initial values, because we're going to need that for finding the difference, and then apply their respective formulas. So we know kinetic energy is just 1/2 mv squared, gravitational potential energy is just mgh, and spring potential is 1/2 ks squared. We then use these to lastly, the change in each value is calculated by subtracting the stored initial value from the updated value. So here's the final output in Python. The model is going to be shown in yellow, and the experimental is shown in blue. So then, using our actual experimental data, we also found the periods. So the period with respect to y in this case was equal to 1.5 seconds, and the period with respect to x was 1.7 seconds. We weren't quite sure why there was this difference, but when asked to predict why this was made, we predicted that because the motion is in a slanted elliptical motion, that could cause for some error in the prediction of the period. So For the second what if question, which is how much work is done by the system, no work is done by the surroundings because all of the objects that we are looking at and considering are inside of our system. So therefore delta, the change in total energy, which is the gravitational potential, spring potential, and kinetic energy, should be 0. And as shown here, when we asked Python to print delta E, the change in energy, it came out to be 0. For the third what if question, which is if you change the origin from the top of the spring to the mass on the spring, what would happen? The change in the origin would only move the length up and down. It would not actually change any of your E values. Because we knew that the relaxed spring length was 0.7 meters, we only had to subtract 0.7 from all the initial Y values. And as shown, the plots remain the same. This is from the original spring, and this is from the spring once we move the position origin down to the mass. So